We've been looking at characteristic equations that produce integers as their solutions, so that when we end up with r equals, say, 3 and -5, we can back up into the solutions of our differential equation and write them as y equals e to the 3t and y equals e to the -5t. So we get these nice integer solutions to our characteristic equation, but they're not always integers. And in this video, we're going to be talking about complex solutions. But before we do that, I'd like to take a minute and talk about non-complex, so therefore real solutions, but that are not integers, because we haven't actually talked about that at all. I'd like to do at least one example. So this is an example of a situation that will return non-integer real numbers as solutions to the characteristic equation. And what do we do with that? Well, it's pretty straightforward. We're going to take the same approach as we did before. We're going to solve this second order differential equation by using the fact that if a solution looks like this, if y equals e to the rt, then y prime is r e to the rt, and y double prime would be r squared e to the rt. We can plug all those into the differential equation, and that would give us y prime, otherwise known as r squared e to the rt, plus 6 times y prime. I think I said y prime before, I meant y double prime. This is y double prime going in here. And then y prime is r e to the rt, and that's a minus 6 times y is e to the rt. And we can factor out the e to the rt, and that leaves us with r squared plus 6r minus 6. And we can factor that or not. In this case, we can't. So I did that the long way again, just to remind you that that's where our characteristic equation is coming from. This r squared plus 6r minus 6 is the characteristic equation. What we're saying here is that this has to equal 0. This factor can never equal 0. And so it's the solutions we get when we set this factor, r squared plus 6r minus 6, when we set that equal to 0, r equals whatever r equals, that's where we get those solutions. So we don't need to write this out every time, but it's important to note that that's what we're doing. R squared is the second power of r, so we have the second derivative of y. 6r is 6 times just the first power of r, so 6 times the first derivative of y, and then minus 6. Oh, there should be a y on that. There should be a y there. So this is the 0th power of r, and this is the 0th derivative of y. So that's where we're getting that equation. So let's take a second now. I'll erase all of this. And let's assume that we remember that and that we know that we can go straight from here to here. I'm going to stop doing that very soon. I just want to make sure we really understand what it is we're doing when we set up a characteristic equation. We're not ignoring the factor of e to the rt in every one of those. We're saying that that factor, to satisfy this equation, that factor would need to be 0, and it can't. Okay, so the other factor is the quadratic, and then we need to solve this quadratic equation. Well, this quadratic equation doesn't factor, so I'm going to use the quadratic formula. I'm going to say r is equal to negative b, negative 6, plus or minus the square root of b squared, that would be 36, minus 4 times a, which is 1, times c, which is negative 6. And that's all over 2a, 2 times 1, so 2. That's negative 6, plus or minus the square root of 36 plus 24 is 60. And that's still all over 2. 60, I'm just going to go over here and do some scratch work. 60 is 6 times 10, 2 times 3. 60 is also 5 times 12, so I could have done it that way. 2 times 5, so I get 2 root 15 here. And then I can put, oh, I never put my 2 in the denominator here. And then I can put that in place of 60, so I have negative 6 plus or minus 2 root 15 over 2, and that reduces to negative 3 plus or minus root 15. Not integers. But I do have two solutions here. I have two solutions to the characteristic equation. So I'm going to have two solutions to my differential equation, two fundamental solutions. I have e to the power of negative 3 plus the square root of 15 and e to the power of negative 3 minus the square root of 15. And that is those are my fundamental solutions. At least I think they are. I know they're not scalar multiples of one another. Right? They're identical except for the sign right here. So one of them is not just a multiple of the other. That's another way to tell whether the Wronskian will be 0. Sometimes it's obvious, like here, and sometimes it's not. So you need to actually compute the Wronskian. If I compute the Wronskian here, I would get e to the negative, oh, I forgot my t here, e to the RT. E to the negative 3 plus root 15 times t for y1. E to the negative 3 minus root 15 times t for r2. And then the derivatives of those are negative 3 plus root 15 times e to the negative 3 plus root 15 times t, and negative 3 minus root 15 times e to the negative 3 minus root 15 t. And the determinant of that array, that matrix, is this product, which is negative 3 minus root 15 times e to the, we're multiplying terms with, or multiplying factors with like bases, so we add the exponents, and we get negative 3 plus root 15t plus negative 3 minus root 15t, which is negative 6t. And then we're going to subtract this product, and that is negative 3 plus root 15 times e to the negative 6t plus root 15t minus root 15t. So we get this. So let's distribute our e to the negative 6t and distribute our negative. We get negative 3 e to the negative 6t minus root 15 e to the negative 6t plus 3 e to the negative 6t minus root 15 e to the negative 6t. These terms combine to 0, and we're left with negative 2 root 15 e to the negative 6t. And no matter what t is, this factor can never be 0. This factor is not 0. So this solution, this Wronskian, is not 0. And what that tells me is that this pair of solutions here is a fundamental set of solutions, which means that I can write a general solution as C1 e to the negative 3 plus root 15 t plus C2 times e to the negative 3 minus root 15 t. All right, that's a good review, and I've done this problem with a differential equation whose characteristic equation returns non-integer real numbers, right? So it's kind of a nice in-between problem. It's a little bit untidier than the previous problems we've done, but not quite as untidy as where we're about to go. So this would be my solution here because I don't have any initial values. I don't have any initial conditions. So this is my solutions as far as I can take this one. All right, let's take a look at another one. I'm going to take the same approach. It's a second order linear homogeneous, or homogeneous if you prefer, differential equation. It has constant coefficients rather than functions. So I'm going to jump straight to the characteristic equation, remembering that I'm assuming that my solutions look like this. So I'm assuming this on my way to saying that that means that this must be true. r squared plus 6r plus 13 equals 0. Again, this does not factor, so I'm going to use the quadratic equation. I get r equals -6 plus or minus the square root of 36 minus 4 times 1 times 13 all over 2a, 2 times 1, which is -6 plus or minus the square root of 36 minus, let's see, that's 40 and 12 is 52 all over 2. That's -6 plus or minus the square root of negative, I have to do this over to the side, 36. 12 minus 6 is 6, 4 minus 3 is 1. So I get -16, and that's all over 2. And the square root of 16 is 4, so this gives me -6 plus or minus 4i all over 2, otherwise known as -3 plus or minus 2i. And that tells me, get rid of my scratch work, that my two solutions, or that two fundamental solutions, are y1 equals e to the power of -3 plus 2i, and y2 equals e to the power of -3 minus 2i. So in form, so far, this looks just like the one that we did on the previous screen. Right, we end up with two solutions as a result of using the quadratic formula. Instead of having an I on the previous screen, I had a square root, but at this plus or minus, and so I split that up into the plus version and the minus version of the values of r, and then I always do this. I need to remember that's e to the r t. Keep leaving my t's off. Okay, so I have e to the rt, two versions of e to the rt. Now, again, I can check to see whether those are linearly independent. I can check to see whether their Wronskian is equal to 0. It is not. Just take my word for it rather than take the time to work that out. But I would encourage you to work on the Wronskian for this one. It's an interesting exercise. And so because they are linearly independent, because the Wronskian is non-zero, I can write my general solution as C1 e to the -3 plus 2i times t plus C2 times e to the -3 minus 2i times t. The problem is we don't really know what e to a complex power means. And through the rest of this video, I'm not sure that we're going to come much closer to understanding what it means, but we are going to find a different way to write it, and we're going to learn how to deal with that aspect of an exponent. So how to cope with that. In order to do that, though, I'm going to go to a different screen. I go to a new screen, and I'm going to work a different differential equation. I have my reasons, so bear with me. And then we're going to come back. I won't be able to come back to this screen just because the way the software that I use for recording works. It sets down the slides that I do sequentially. So I'm on slide 7 right now because I'm doing the whole course all at once. But when I finish, I'll ask it to collate slides 6, 7, and 8, and then possibly 9 as well into a single video. I can't come back to slide 7. So what we're going to need to do is we're going to need to remember that we were solving this differential equation, and I'll make a note of that on the screen after the next one so that we don't forget that we had these two fundamental solutions, and then we'll go from there. So on the next screen, I'm going to do a completely different problem with an explanation as to why I'm doing it, and then on the screen after that, we'll come back to this problem. Okay, let's take a look at solving this differential equation. One way we could do it, of course, would be to jump to the characteristic equation. That gives me r squared equals -1, so r equals plus or minus I. That means that my two solutions are y1 equals e to the it, and y2 equals e to the -it. Let's check that those are linearly independent, that they form a fundamental set. We have e to the it and e to the -it. The derivative of e to the it is I e to the it, and the derivative of e to the negative it is negative I e to the negative it. And I want the determinant of that, which is this product minus this product. So my first product there is negative I times e to the it times e to the negative it, or e to the it minus it, or e to the 0. And the second product, I'm going to subtract I times e to the it plus e to the, times e to the negative it, so e to the it minus it, which is 0. So that gives me negative I times 1 minus I times 1, which is negative 2I, which is not 0. Therefore, these two solutions, where's my highlighter? These two solutions comprise a fundamental set of solutions for that differential equation. And I can write that as y equals c1 e to the it plus c2 e to the negative it. All right. Now we have initial conditions this time, so let's see what happens with those. When I now have an expression for y, for my solution, right? So I have a y, and I have, on the right-hand side, I have an expression that has some t's in it. So I can plug these two values in, and I get y, which is 2, equals c1 e to the I times 0, which is 0, plus c2 e to the negative I times 0. That gives me 2 equals c1 plus c2. Okay, that is this set of initial conditions. Now I need to deal with this set of initial conditions, but I don't have a y prime. I have a y, so if I take the derivative of that, I'll get y prime equals c1 times I times e to the it plus c2 times negative I. So let me change this to a minus. It's the easiest way to deal with that. Times I times e to the negative it. And I'm going to plug these initial conditions into this equation. That gives me y prime, which is 0, equals c1 times I times e to the I times 0 minus c2 times I times e to the I times 0. So 0 equals I times c1 minus I times c2. If I take my two equations, I get 2 equals c1 plus c2, and 0 equals I c1 minus I c2. And I solve this system of equations. I might do that by multiplying through by I here. Start with that, 2I. If I add those together, I get 2I equals 2I c1, and these terms cancel. That was the whole point. Dividing both of these by 2I, 2I gives me 1 equals c1. And since I know 1 equals c1, I can plug that into, this is probably the simplest equation. If I plug 1 in for c1, I'm going to get that c2 also equals 1. Well, that's handy. Get the right pen here. So 1 equals c2 as well. That information lets me know that my particular solution is y, where's my pen? Y equals c1, which I now know to be 1, times e to the it plus c2, which is also 1, e to the negative it. So, where's my pointer? The solution to this differential equation with these initial conditions is this equation right here. Y equals e to the it plus e to the negative it. Okay, well that's interesting, but there's more to it than that. I'm going to see about moving a few things around here. I definitely want to hang on to that. Maybe I'll put that up here. And let's draw a line under this. And I think I might need to erase some of this screen. I think that's probably the best approach here. All this is all scratch work, right? On a quiz or a test, certainly on an exam, I would expect to see all of this work. I'm going to erase it because I want you to have the instruction of seeing how it's done and then seeing the result of that. But also I want on the same screen this solution here and the other solution that I'm going to show you in a minute. And so I want those both on the same screen kind of at the same time. And so let's see, maybe I don't have to erase everything. Okay, I've erased a little bit of my work solving the system here, but I've left most of the rest of it, and I've moved my final answer to this approach up here. So this is my ultimate solution from this approach to the differential equation that I'm trying to solve. There's another approach though, and I think this is really quite interesting. I'm going to rewrite my differential equation. I'll do it here. Y double prime plus y equals 0. And if I subtract y double prime from both sides, I get y equals negative y double prime. Now, when we first started learning how to solve second order differential equations, I asked you just to imagine for the moment what kind of equations had a derivative, what kind of functions had a derivative that was equal to or very close to the original function. And we very quickly came up with the idea that e to the t or e to the x was such a function, right? You take the derivative of e to the x, you can do it forever. You're going to get e to the x every time. Well, we can use that idea here, but we can also use a slightly different idea. If we look at this version of this differential equation, we might ask ourselves instead, what functions are out there which, when you take their derivative twice, they stay the same function but change sign? And those functions, the ones that come to mind for me anyway, are sine and cosine. So, for example, if y equals the sine of t, then y prime equals the cosine of t, and y double prime equals negative the sine of t. And with that, we have y, which is sine, equals negative y double prime, which is negative sine. Cosine does the same thing. If y equals cosine of t, y prime is negative sine of t, and y double prime equals negative cosine of t. So once again, y is equal to the opposite of y double prime. Okay, so these two functions are also now potential ways to approach solving this equation, because if what I want is for y double prime plus y to be 0, then I can take y double prime plus y to be equal to negative the cosine of t plus the cosine of t, and sure enough, I get 0. So that is a solution. The same is true of sine. Y double prime is negative sine. Y, the original y there in that case was sine, and that is also 0. Now, for historical reasons, we're going to use the cosine version of this. Historically, the way what we're going to do now is describe some experimentation that Leonhard Euler did in the 1700s to come up with a different way to write e to a complex power, or e to an imaginary power anyway, okay? And when he was working on this, he was doing it in the context of solving a particular application. He was working on harmonic problem of harmonics. And so in that setting, he had not just initial conditions, but an actual specific setting. And so when he set down the equation that he was playing with, differential equations and certainly complex exponents being a relatively new thing, he was working with cosine. So we're going to stick with cosine so that your textbook and what you learn here in this video and all of history kind of line up. Could you do it with sine? I believe so, but we're going to stick with cosine. So if we argue then that a solution to this equation is negative the cosine of t, is the cosine of t, y equals the cosine of t, then the next step is to recognize that that's not the only solution. And if you'll recall from the principle of superposition, we can have multiples. I should probably use something other than c here because c and cosine are confusing. I'll use k. If y equals the cosine of t is a solution to this differential equation, then y equals some multiple of the cosine of t is also a solution. And we're looking for a particular solution here. We have initial conditions. So let's plug our first initial set of initial conditions in. When t is 0, y is 2. Well, the cosine of 0 is 1. So k equals 2. And that means that y equals 2 cosine of t satisfies this differential equation with these initial conditions. Y prime is, if that's y prime is 2 times negative the sine of t. And we have 0 equals 2 times negative the sine of 0. And that's just 0 equals 2 times 0, which is true. We haven't learned anything new from this, but we have verified that the solution we're proposing, this one right here, still satisfies both sets of initial conditions, which is important. So we now have a solution based on a completely different approach, and it looks completely different. So let's take a minute and tidy things up. I'm going to move, actually I'll just write this up here. Y equals e to the it plus e to the negative it, and also y equals 2 cosine of t. All right, so I'll highlight that one as well. That's another solution to this differential equation. All right, at this point, there is kind of a next step to this. So at this point, I am going to erase this screen because I want to keep this information here. I want to carry on with what I've got here. All you see here on this screen is what we did to get to these two solutions. So if you need a minute to pause and take some more notes, finish writing things out before we go on, then please feel free to do that. Pause the video. And when I come back, this screen will be almost blank except for this top line up here, and we'll carry on from there. Okay, so now we have two very different looking solutions based on two very different approaches to the same differential equation. So it would be easy and very believable to argue that those two things must be equal. So let's set them equal to each other and see what happens. 2 times the cosine of t equals e to the it plus e to the negative it. Well, there's nothing obvious here that tells us what we might try next, but I wonder if, since we're dealing with derivatives and differentials, if maybe we should take the derivative of both sides of this and see what happens. The derivative of 2 cosine t is negative 2 the sine of t, and the derivative of the right-hand side will be I e to the it minus I e to the negative it. Well, there's still nothing really obvious here, except that with the exception of this I and the sine, these two terms are the same. These two terms are also the same except for the I. But I'm particularly intrigued by this one because if we could get rid of the negative I, somehow that tells me things might simplify a little bit. The problem is this I right here. I can't just add these two terms together and have them disappear. What I can do is divide all three of these terms, divide both sides, and therefore divide all three of these terms by I. That gives me -2, the sine of t over I, equals e to the it minus e to the negative it. Well, what's going on here? What does it mean to divide by I? Let's do a little scratch work over here. If I take 1 divided by I, that's really 1 divided by the square root of -1. That's what I means. And then if I rationalize this, I get -1 over root -1 over root -1. That's the root of -1 over the square root of -1 squared, which is -1. That's I squared, which is -1. And so that is negative the square root of -1, which is -I. So 1 over I is equal to -I. Cool. So let's change this to -2 times -I, the sine of t. And that's equal to e to the it minus e to the negative it. And then, of course, a negative times a negative is a positive, so that gives me 2I sine of t equals e to the it minus e to the negative it. And now, this is all tidied up, but in addition to that, if I bring my cosine equation down, just go ahead and copy that down here, 2 cosine of t equals e to the it plus e to the negative it, and I add these together, these terms now cancel out. And I have 2 cosine of t, there's a reason I'm doing it in that order, plus 2I sine of t equals 2 e to the it. And of course, everything's divisible by 2. So I'll write this as cosine of t plus I sine of t equals e to the it. And that is called Euler's formula. This is a very powerful, very useful in certain contexts. Certainly it's going to be useful to us in a few minutes here. But this is a very powerful, very well-known formula in mathematics. If you take a lot of mathematics, if you take really almost any mathematics beyond this, you're pretty much guaranteed to see it at some point. But what we're interested in now is how we can use this formula to further our exploration of what happens when we have complex solutions to our characteristic equation of differential equations. Before we dive in too much into that, though, I'm going to make a list of variations of this formula. We have this one, cosine of t plus I sine of t equals e to the it. It turns out if you have something like, actually, let me rewrite that. I'm going to write this so that the e to the it is over on the left-hand side. E to the it. And the main reason for that is simply that this is usually how we're going to see things, and we're going to want to rewrite them in this form. All right, if we have e to the ait, where a is a real number, then that changes this side to the cosine of at plus I times the sine of at. That's going to be important in when we go back to the problem we were originally trying to solve here. One other thing to note is that e to the a plus bi times t can be written as e to the a times e to the at plus e to the bit. I guess I could put parentheses around that. And that means I'm going to have e to the at times, how do we write e to the bit? We write e to the bit like this. I've confused my letters here, but it's what position it's in that's important, right? So I'm going to change this piece right here so that it's in this form. So I'll have the cosine of bt plus I times the sine of bt. So now this piece right here, the pieces that are highlighted in white, those are equivalent. Right? They're two different ways to write the same thing. So this is a pretty powerful statement. We have something that, if we have something that looks like this, we can write it in this form. And that's exactly where we were in the previous problem. We had something that kind of looked like this. We had an A plus BI and an A minus BI solution. We had two solutions that looked like this. And so now we can go back and rewrite them in this form. So let's do that next. There's another step we need to consider after this, but let's get to that point first. I'm going to on the next slide, I'm going to recopy the solutions that we came up, the differential equation that we were trying to solve, the equations that we came up with, the point to which we had arrived when we stopped to come and look at this differential equation. So on the next slide, you'll see our old problem back again with its solutions at that stage. Okay, here's our differential equation that we were trying to solve. We had done one before this where the roots of the characteristic equation were not integers, but they were still real numbers. With this one, we came up with solutions to the characteristic equation that were -3 plus or minus 2i. And when we plugged them in, we got these two solutions, y1 and y2, to the differential equation. But then we were asking ourselves, what on earth does it mean to have e raised to an exponent that has a complex number in it? Well, now we know not necessarily what that means, but at least another way to represent it. So one thing we could do with this is simply to change the form that our general solution is in. We have C1 e to the -3t, as I explained on the previous screen, e to the 2it plus C2 e to the -3 t. I keep leaving that t off. E to the -2i t. And then we can write the e to the 2it part as the cosine of 2t plus I times the sine of 2t. Plus, then we have C2 e to the -3t times the cosine of -2t plus I times the sine of -2t. That is certainly one approach. If we had initial conditions, we would go back and try to figure out what the constant values here were. We don't, at this point in this problem, have those initial conditions. So we are just trying to find a general solution. And it appears on the surface that we have one. We do, in fact, have one. But here's an interesting thing. There's a theorem. It's 3.2.6 in our textbook. And if you are in our textbook, at least in this edition, it's page 117. And we didn't address this when we were talking about section 3.2 because it didn't really seem to make sense at that point. But now it really does. It says that if you have a second order differential equation, a homogeneous differential equation, where P and Q are continuous real valued functions, that's an important constraint, but all of our functions will meet that. Then if we have a solution, y equals u of t plus I v of t, then the function u of t, which is the real part of the overall solution, and v of t, not I v of t, just v of t, which is the coefficient, or well, it's a functional coefficient. It's the b in the a plus bi, right? It doesn't include the b, it doesn't include the I, it only includes the function. That function right there is also a solution. U and v are also solutions. So let's take a look at just one of these equations, one of these solutions, rather than looking at this whole big one here. Let's just take y1. Let's just start with that. Notice that y1 is e to the -3 plus 2i times t, and that's what I have without the c1 in front of it. That's what I have here. It's the first term in this general solution. So it's the first term in this form of the general solution. So it's the first term in this form of the general solution. So what I'm essentially saying is that without having to go through all the algebra again, I can write y1 as e to the negative 3t times the cosine of 2t plus I times the sine of 2t. And I've left off the C1 here because I'm just working with y1. I'm just transforming the way that I write the exponent here. Instead of a sum, I have a product with common bases. And then I've transformed the form that this e is in to this here. So I'm leaving that C1 off because I'm not dealing with the whole thing, just y1, and so it doesn't have that C1 in front of it. So I'm going to highlight this as well because that's a different form of y1. So the two highlighted things here, not including the theorem, and these two highlighted things here are equivalent. All right, now if I distribute, I get y1 equals e to the negative 3t times the cosine of 2t plus e to the negative 3t times I times the sine of 2t. And if I rearrange those, put the I in front, then essentially here I have an A plus BI, right? I have a complex number. I don't know what T is yet. At the moment, T could be anything in the domain, but the idea is that I have a complex solution here, and more importantly, I have a solution in this form. I have a y equals, it's y1, but it's a y equals a function of t plus I times another function of t. So this function of t is my u. Let me change my a and b to u of t and v of t. And what this theorem says is that that means that y, let's call it y3, equals just the e to the negative 3t cosine of 2t is one solution, and another solution is e to the negative 3t times the sine of 2t without the I. That's pretty powerful stuff. If y equals u plus iv is a general solution, then just the u of t and just the v of t without the I is also a solution, are also solutions. So here, this is my u and this is my v, no I. So now, ideally, what we would have with this is a fundamental set of solutions. And the way to determine whether it's a fundamental set of solutions is to find the Wronskian. Well, I set out to do that a minute ago, and I had to back up and erase everything I had done because it got so big and so messy that it was really quite challenging. But I will say that it's challenging to get it all on the screen. I couldn't fit it on the screen. Actually, taking the Wronskian here is not a difficult thing to do, but there's a lot of algebra involved, and it is big. It takes a lot of space. So I'm not going to do that here, but if you will, again, trust me and take my word for it, that the Wronskian is not zero, then what that means is that these two solutions that we came up with, y3 and y4, are a fundamental set of solutions. For those of you who have had some linear algebra, what that means is that they span the entirety of all the solutions to this differential equation. So I now can write a general solution, y equals c1 e to the negative 3t cosine of 2t plus c2 e to the negative 3t sine of 2t. And then, of course, if you wanted to, you could factor out that e to the negative 3t, and you'd have c1 cosine 2t plus c2 sine of 2t, but it's not really necessary. So I'm going to highlight this one as my right color here. This one is my final solution to this differential equation. I don't have initial conditions, so I can't find a particular solution. This is my general solution. Now this is actually question number 8 in section 3.3 of your textbook. So it's an even number problem. This textbook gives the answers to all of the problems in the back, but I still tend to, mostly out of habit, I still tend to assign mostly odds. And that way, when you're just doing daily practice, you can check your answers, make sure that you're on the right track. And if you're not, then you can go figure out what went wrong. So this is an even number problem. It's unlikely that you would see this one in an assignment, but you might see one like it. One more thing here, and this is actually kind of a nice culmination. It brings everything together. It turns out that when we have a differential equation like this that only has real valued coefficients, we really kind of want our solutions to only have real values in them. So ideally, we kind of want a way to get rid of the I, even though we've used it to get to this place, to get ultimately to this place, we sort of want each time to get rid of the I if possible. And so we're going to use that theorem that we talked about here, this theorem 3.2.6, and we're going to state a very general result from all of this. If your differential equation has roots r equals a plus or minus bi, and I'm going to write this as ib just because this is how we're now seeing the I, right? It's kind of appearing at the beginning of this term here. And this is how it's written in your textbook. Your textbook uses Greek letters, lambda and mu instead of a and b. But with that aside, it turns out that your u of t is going to be e to the at cosine of bt, and v of t will be e to the at the sine of bt. And that is exactly what we got. Where am I? Here. Y is equal to e to the at. A was, my roots were -3, r equals -3 plus or minus 2i, right? Those were my roots. Those are the roots of the characteristic equation. So my a is -3 and my b is 2. And ultimately my solution, my u and my v, were a was -3, e to the ab, cosine of bt, b was 2. And my v function, v of t, was e to the at sine of bt. B was 2, a was -3. So, and then when I put these together, I add the C1 and the C2, and if I have initial conditions, I might be able to take it a step further. But this result right here is the result that you will most likely use to actually solve these problems. And it's taken us almost an hour to get to this shortcut, but that's okay because I hope that you now understand why this shortcut exists. If the solutions to your characteristic equation are complex numbers, then your functions u and v, which get used here, u and v become, u and v, it turns out, are a complete set of fundamental solutions. Then you have your u and your v, you can put them together into a general solution. So this is most likely how you'll proceed from now on, but how does this come to be? How can you just take the a and throw it in the exponent and the b and put it in a cosine and a sine and call it good? Well, the last hour, I hope, has explained why that is. Well, that's going to do it for this one. Thank goodness, you're all saying. In the next video, we're going to be talking about what happens when you have real roots, again, even integers possibly, but when they're the same. When you have two roots that are the same, what happens then?